Hello. Let's wait for some time for others to join, then we can start the session. Can someone confirm if I am audible and the screen is visible?
Yes, sir.
Okay, thank you. Okay, I think we can start the session. So, welcome everyone. My name is Arpit Bal and I am a PhD scholar from Department of Electrical Engineering, IIT Bombay. And so, in the previous live sessions, what we covered is related to introduction to number systems, then basic Boolean algebra, floating point representation, and we also solved a few problems related to combinational circuits. So combinational circuits are the circuits which don't have a memory, like they depend on the current input itself, right? There is no storage element involved. But in today's session, what we are going to solve is related to something called as a sequential circuit. So in sequential circuit, there is a memory element involved which can either store the previous output or previous state. Okay. So with this basic introduction, we can start today's live session. And so if you have any doubt, so you can unmute yourself and ask. Okay. Please feel free to ask your doubts. Okay, so the first question is, we have a 1 megahertz clock that is applied to a JK flip-flop, and the inputs to the JK flip-flop is J is equal to 1 and K is equal to 1. So we have to determine what is the frequency of the flip-flop output signal. Okay, so let us first see what does J is equal to 1 and K is equal to 1 does. So let me write down JK Q plus, where Q refers to the present state and Q plus refers to the next state. Okay, so when the input is 0 0 and let's say the Q is 0, then the next state is going to be 0. Similarly for 0 0 1, the next state is going to be 1. So it means whenever J and K are both 0, whatever is the Q, it will get reflected in the next state. Okay, so let me write it like this. If J is 0, K is 0, Q plus is going to be Q. Okay, so next is 0 1. So whenever, okay, let me write it completely. Okay, so the next thing is whenever J and K, when J is equal to 0 and K is equal to 1, then the next state is going to be 0 irrespective of whatever the value the present state is. Okay, so 0 1 implies 0. Okay, then the next thing is 1 0 0. Okay, so it means whenever J is equal to 1 and K is equal to 0, the next state is going to be 1 irrespective of whatever the value the present state was. Okay, so the next thing is, if J is equal to 1 and K is equal to 1. Okay, so observe this particular point because this is related to our question number 1. Okay, so here what we see, that if J, K both are 1, then what happens is whatever is the present state, okay, so that is being flipped. Okay, if present state is 0, it becomes 1, and if it is 1, it becomes 0. Okay, so 1 1 means Q bar, right? So now what we are asked is, what is the frequency of the flip-flop output signal? Okay, so we have the flip-flop, J is equal to 1, K is equal to 1, and we have a clock signal. What is the frequency of the clock signal? It is mentioned that it is 1 megahertz. Okay, so for these type of questions, what you need to do is you need to make yourself comfortable in drawing timing diagrams. Okay, so the first thing in the timing diagram that you need to draw is a clock. Okay, so this is our clock. Okay, and let us assume that every positive edge, the output is reflected. Okay, and let us assume initially the Q or the output was 0. Okay, so if it is 0 initially, whenever the clock arrives, because J is equal to 1, K is equal to 1, so the next state will always be Q bar. So if it is 0 initially, whenever the clock arrives, it is going to toggle. So it will be 1. It will be 1 till what point? Till the next clock edge arrives. Because once the next clock edge arrives, it needs to change its state. Okay, so it will change its states from 1 from 0. So again, when we get another clock edge, it will change its state again, right? And it will again change its state when another positive edge of the clock arrives. Okay, and then this will go on, right? And what is given to us, that the frequency, okay, so you can observe it here, that this portion is actually 2t. Okay, if this is t, fine. So t is nothing but 1 by f, so 2t will be 2 by f. In other words, we can say that the output q has a frequency f by 2, where f is the frequency of the clock. Okay,
500 kilohertz, I think.
correct. So it will be 1 megahertz by 2, that is 500 kilohertz. So option B is the correct answer. So does anyone have any doubt in this question? Okay, if not, then okay, let me mention one application of this circuit. So this circuit can be used to generate any lower form of clock. Like, let's say we have a very high frequency clock, but a module in our circuit needs a clock at a very low rate. So we can use a JK flip-flop in this fashion to generate that particular frequency. Okay, so this is one application. And okay, so another thing is, so let's say I have this particular flip-flop. Okay, so now I know that if I apply a clock here, f clock, and it is connected in this fashion, that j is equal to 1 and k is equal to 1. So whatever output I will be receiving is going to be f clock by 2. Right? So what will happen if I use this output as a clock to another flip-flop? What will be this frequency? Can anyone answer?
F by 4.
Correct. So it will be f clock by 4. Similarly, if you want any number of division of this particular frequency, so that many number of flip-flops you need to use, and you need to connect it in this fashion. Okay, so here you can observe that if we had one flip-flop, then it was getting divided by f clock by 2. If we had two flip-flop, then the clock was getting divided by 4. So we can say that we can perform clock division in this fashion, so where n represents the number of flip-flops that are being cascaded in this way. Okay, so you will find this useful when you are dealing with higher number of flip-flops. So for 1 and 2 it is fine. Let's say I would have given a very bigger number. So the one thing that you could have done is you find out what is this particular frequency, then this particular frequency, or else you can directly use this formula. So I hope this thing is clear. Okay.
Yes.
So does anyone have any doubt in this question? Okay. So I am assuming that this is clear. So okay, let's move on to the next question. Okay. So the next question is, how many flip-flop circuits are needed to construct mod 16 counter? Okay. So okay, let me explain what mod 16 counter is. So mod 16 counter means that it will count from 0 to 15. So the total number of states here is 16, right? Including 0. So that's why it is called as a mod 16 counter. And once it counts, the count reaches 15, then it will go back to 0 again, and the count will be repeated. Okay. So here, whenever you are given a question like this, mod 16, okay, so it can be anything, mod, we can call it mod k. Okay, so the first thing that you need to figure out is how many bits are required to represent this k. Okay, so in our case, what is the last state? That is going to be 15. to represent 15 in binary, how many bits we need?
4.
Correct. Okay, so we will need 4 bits. So the count is actually from 0000 to 1111. Okay, so because we need 4 bits, so we will need 4 flip-flops to store those 4 bits. Okay, this is flip-flop 1, 2, 3 and 4. Okay, so the answer to this question is 4 flip-flops. Okay, so here there is another general formula. So let's say 2 to the power n should be greater than equal to 16. Okay, so here you have to figure out for what minimum value of n this condition is being satisfied. Okay, so let's say if it was given to you that it is 2 to the power okay, so let's say I am saying it is mod 14 counter. So you just need to write 2 to the power n should be greater than equal to 14, and then you solve this equality for the equality 2 to the power n equal to 14. Whatever value you get, you find the nearest integer so as this condition is satisfied. Okay, so you can use this formula as well. Otherwise, if you want to do it logically, you can do it logically in this fashion as well. Okay, so this question is clear, I am assuming. So moving on to the next question. So in this question, what is given to us is a D flip-flop. Okay, and the input to that D flip-flop is actually the Q bar. Okay, and we need to figure out what is the behavior of this circuit. Okay, so the first step whenever we see this circuit, whenever we see any form of circuit, is to either draw the timing diagram, or if it is convenient, then we can go for a truth table as well. Okay, so whichever we can find easy, we just need to pick that. So in this case, what I am going to do is I am going to use truth table to determine the logic. Okay, and in truth table I'll also write clock as an input just for the sake of reference. D, Q is the output, and then Q bar. Okay, and here we know that D is actually equal to Q bar, right? Because this Q bar is being fed to D as an input. So let us assume that initially everything was 0. Okay, yeah, so if Q is 0, Q bar is 1, right? So when the next clock arrives, what will be the value of D?
1.
Yeah, the value of D will be the previous value of Q bar, so that is
Yes.
1. And then the Q's value will be 1 because Q is directly Q is equal to D, and then what will happen is the Q bar will be 0 because Q is 1.
0.
Yeah. So what will happen in the next clock edge? What will be the value of D?
Again it will be 0.
Correct. Again it will be 0 because Q bar is 0, and that is getting reflected at D. And the next value of Q will be
0.
correct, and Q bar will be 1.
Again 1. Yeah.
And this pattern will go on repeating and repeating. Okay, so let us see what is happening here. So let me draw my clock. Okay, let me mark the, I am assuming it to be a positive edge triggered. Okay, so this is my clock, and what is happening to my Q is initially it was 0. When the first clock arrived, it became 1. Then it stayed. When the next clock arrived, it became 0. Okay, then it goes on repeating this pattern. Okay, so we observe that Q is 0, 1, 0, 1, 0, and so on and so forth, right? So option A is wrong because q is equal to 1 always, that's not true. Option B is also wrong, q is equal to 0 always is not true. Okay, so now comes to option C, acts as 1 bit counter. Okay, so what will 1 bit counter count from 0 to 1, right? Then again it will go back to 0. And we are observing that this is the exact behavior that Q is following. So this option C is correct, that it is a 1 bit counter. Okay, I hope this question is clear for everyone. So I'll wait for a minute. If anyone has any doubt, then they can ask me for this particular question. Is everyone clear with this question? Okay, great. Okay, then we will move to the next question. Question number 4. Okay. So this is actually kind of an extension of question number 1. Okay. So what does T flip-flop do when T is equal to 1? Can anyone answer? Okay, so let's say this is the T flip-flop. Okay, so whenever T is equal to 1, what happens is Q plus is actually Q bar. Okay, and whenever T is equal to 0, Q plus is Q. Okay, so Q plus represents my next state. Okay, Q bar is the complement of the present state and Q is the present state. Okay, so whenever I am saying T is equal to 1, so T is equal to 1 will refer to J is equal to 1 and K is equal to 1 wala condition. Okay, the question, okay, that is exactly same as question number 1's condition, J is equal to 1, K is equal to 1. Okay, so you can think of it as a JK flip-flop, okay, that is taking 1 kilohertz as the input. Okay, and we observed what was the behavior of the circuit in the question, in the first question, right? So what is going to be the frequency at the output of first flip-flop? Can anyone answer?
Sorry, please repeat.
Yeah, so what is going to be the output at this particular node? At the output of the first flip-flop, what is going to be the frequency?
Half of 1 kilohertz, that is
correct.
500.
Yeah, that is 500 hertz. Okay, similarly, so that 500 hertz is being used as a clock for the second flip-flop, and the input to the second flip-flop T2 is equal to 1. So what is going to be the output frequency at the end of second flip-flop?
250. End of second, 250 hertz.
Yeah, 250 hertz. Okay, similarly, what is going to be at the output clock frequency of the last flip-flop?
That 125 hertz.
Yes, that's correct. So 125 hertz is the answer. Okay, so similarly, if you find any number of flip-flops that are cascaded in this way, you can figure out what is going to be the frequency. Otherwise, you can directly use the formula, that was Fn by 2 to the power n. In this case, n is equal to 3. So it is Fn by 2 to the power 3, that is Fn by 8 or 1000 by 8. That will be 125. Okay, so I hope everyone is clear with this question number 4. And yeah, so these things you need to actually remember. for T what is going to be the condition, for J, K what is going to be the condition, and for D. So these three are important ones because they will help you in developing further complicated circuits. Okay, so I hope question 4 is clear. If anyone has any doubt in question 4, they can feel free to unmute themselves and ask me. Okay, if not, then we can proceed with the next question. Okay, so in question number 5, what we are given is we have two counters. Okay, so up count. Okay, so there are several form of counters. So one of them is a up counter. So up counter counts in upward direction. So when I say upward direction, it means it will be incrementing. So let's say it starts from 0, then it will go to 1, then it will go to 2, then it will go to 3. So it is moving in an increasing direction, right? So that's why it is called as an up counter. Next is mod 2 and mod 5, right? So what does mod 2 represent? So mod 2 means there will be two states. Okay, if the states start from 0, then I will have 0 and 1. Similarly, mod 5 means there will be total 5 states. Okay, so for representing 5 states, how many flip-flop I will need?
Sorry, please repeat the question.
So I have to represent 5 states.
Yes.
So to represent 5 states, how many flip-flops will I need?
Three.
5, 3 or...
Correct, yeah. So 3 because yeah, so mod 5 means it will reach from 0 to 4, and 4 will need 3 bit for representing 100. Okay, so here we will need 3 flip-flops. Okay, I hope this point is clear. We did a similar problem in question number 2. Okay, so here what the question is asking, that there is a mod 2 flip-flop and there is another mod 5 flip-flop, and they are cascaded together. Okay, so we need to find out what is the resultant flip-flop that this is going to represent. Sorry, resultant counter that it is going to represent. Okay, so let me call it mod X counter. Okay, so now let me draw the timing diagram for better understanding. So I'll start the timing diagram with a clock. Okay, okay, so what is going to be the mod 2 counters waveform? When it is 1, let us assume that it is 0. When the next clock edge arrives, it becomes 1. When the next clock edge arrives, it becomes 0. At the next clock edge, it is 1. Then again 0. Then again 1. Then again 0. Then again 1, 0. And so on and so forth. Okay. Right? Then output of mod 2 is going to be fed to mod 5 counter. Okay, so mod 2 counter, what it did, it counted the clock pulses, right? So here it was only the first clock, so nothing, and in the second clock, that's why it became toggled, right? So then here it is again 0, then it toggles to 1. So it is basically flipping between 0 and 1, 0 and 1, like that. Okay, so now the mod 5 counter, let us assume that it was 0 from the beginning. Then when it gets the first clock edge, it is going to become 1, and it is going to count till 5. Okay, so this is 0, 1, 2, 3, 4. Okay, so these are total 5 states, right? So 0, 1, 2, 3, 4. So once it crosses 0, 1, 2, 3, 4, then it is going to change its state. Okay, so what is the total number of clock pulses that it took? Okay, because you can see mod 2 took 2 pulses, that's why it is called as mod 2. Mod 5 took 5 pulses from mod 2, that's why it was called as mod 5. But what is it representing in the resultant format? Okay, like if I directly apply f clock to this thing, what is the output being called as? Fx. Okay, so you can observe that it is taking 10 clock cycles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then after that it is changing its state, right? So this is actually a mod 10 counter, correct, that it is counting 10 pulses. Okay, so in short the formula is, if you are cascading two counters A, like mod A and mod B, then the resultant that will generate mod X will be mod of A into B. Okay, so this is the formula and this is the logic behind that formula. I hope that portion is clear. Okay. Does anyone have any doubt in this question? So I'll suggest you to, before attempting this question, so I'll suggest you to be comfortable in drawing the clock diagrams, the timing diagrams, so that it will be helpful for you to figure out how we are arriving at this particular formula, because simply remembering the formula won't be helpful in the longer run. So I'll suggest you to first get acquainted with this logic and then use this formula. Yeah, when you have less time, you can directly go for this formula, that's not an issue, but yeah, this is the logic behind this. Okay, so we will move to the next question. Okay, so the next question is, the output of a JK flip-flop with asynchronous preset and clear inputs is 1. Okay, so it means that, let's say JK, Q is given as 1. The output can be changed to 0, so it means the next state is going to be 0 with one of the following conditions. Okay, and you have to tell me in which condition can Q plus be 0. Okay, so we saw the JK flip-flop table in the first question. So using that table, can anyone tell me what value can I assign here for JK?
J equals to 0.
Okay.
And K equals to 1.
Okay. Okay, is there any other possibility?
If both are 1, 1.
Okay.
Then also one possibility
Yeah,
is there.
that's correct. So these two are the possibilities that J and K can occupy, so that the present state changes into 0. Right? So if J is equal to 0, K is equal to 1, Q plus is going to be 0 irrespective of what Q is. Okay? And when J is equal to 1 and K is equal to 1, Q plus is going to be the complement of Q. And because in this state we know that Q is equal to 1, So it is going to turn to 0. Okay, so let us see what are the options that are present. Okay, so we have this option j is equal to 1 and k is equal to 1. So option B is correct.
Yeah, please repeat because I'm able to hear your voice was cracking that time.
Oh,
Yeah, please explain it. Yeah.
okay, sure. Yeah. So here, so the two possibilities are 0 for j is equal to 0, k is equal to 1. So the next state of q is going to be 0 irrespective of what the present state is. Right? Similarly, if j is equal to 1 and k is equal to 1, then our next state is going to be the complement of the present state. And because in our present state it was 1, so the next state is going to be 0. So these two possibilities are correct, and in the options we have this particular possibility available, that j is equal to 1 and k is equal to 1. So that is the correct answer, option B. Is that clear?
Okay. Yeah. Yes.
Okay,
No.
yeah,
It's clear.
thanks. So does anyone have any doubt in this question? Okay, so we'll move on to the next question, that is question number 6. Okay, so yeah, so I'll give you a moment to read this question first. Okay, and yeah, so you have to, so the first thing I want you to do is to understand this question. So what does this question want you to answer? Okay, so take 1 minute and try to read through the question. Okay, then I'll explain what this question actually means, and then you can solve. Then we'll start solving. Okay, so give it a read for a minute. Okay, I hope everyone has given it a read. So can anyone explain what this question wants from us? Anyone can explain, like don't be afraid to be wrong, so that is fine. No, first try to explain what does this question want. Amit, would you like to explain?
Yes, sir.
Yeah.
Hello.
Yeah, Amit.
In case of the D flip flop, output follow the inputs.
Okay.
Hello.
Yeah.
And in case of the D flip flop, output follow the input.
Correct.
Yes, sir.
But what does this question want us to answer? Like, yeah, you are correct. But this particular question, what is it trying to mention?
मीन्स जो सर आउटपुट जो भी आउटपुट होगा वो एज ए इनपुट ही होगा जी.
हाँ वो सही है. Okay, so let me explain this question once. Okay, so what this question is saying is that the output QBQA, it is going through the following sequence. Okay, 0 0 1 1 0 1 1 0. Okay, so what is happening is we need to figure out what, so we have two flip-flops available, two D flip-flops, and we need to figure out what is going to be the input to this D flip-flops so that we arrive at this particular sequence. Okay, and to arrive at this particular sequence, a transition table has been mentioned. Okay, that when the present state is 0 0, the next state is going to be 0 1. Okay, and when the next state is 1 1, sorry, when the present state becomes 1 1, the next state will be 0 1. Okay, then the next state becomes present state, that is 0 1. So at that moment the next state will be 1 0, and once it is 1 0, then it comes back to 0 0. Okay, and how do we arrive at these states? So we are using D flip-flops. Okay, so because 2 bits are involved, so we will be using 2 D flip-flops, that is DA and DB. Okay, so now let me write down. Okay, let me write down what are going to be the. Okay, so this is present state, so I'll write QB QA. Okay, this is the next state, so I will write QB plus and QA plus. Okay, then I'll write the input to the D flip-flop as DB DA. Okay, so the present state is 0 0, next state is 1 1. Okay, as Amit correctly mentioned, that D flip-flop, whatever you give as input, that is going to reflect as output. So what is going to be the input for this case? Can anyone tell me what is DBDA? What should I give input to the D flip-flop so that I arrive at 1 1 as the output?
1.
Correct. So DB is 1. Yeah, 1 1. Okay. So the next state is 1 1. It is becoming 0 1. Okay. So in that case, what should be the D input?
0 1 0 and 1.
Correct. 0 and 1. So basically whatever we are going to write in the next state, we will copy it exactly in the D in. Okay. So the next state, let me write it as 0 1. Okay. And it is changing into 1 0. And this next state
So
we
it
are
will
going
be
to
1
copy
0.
it. Correct. That is 1 0. Again it will be 1 0. It is 0 0. So D will be 0 0. Okay. So now we have to actually mention D in as a function of the present state. Fine. So what does 0 0 correspond in binary? This is 0. 1 1 corresponds to 3. 0 1 corresponds to 1. 1 0 corresponds to 2. Okay. So now let us focus at DB. So DB can be written as summation of. Okay, so this is 1. Sorry, this is 0. And this is 1. So DB can be written as summation of 0 comma 1. So everyone got this point?
Yes.
Okay. Okay. So what we need to do is we have to mention DB and DA as a function of QB and QA. Okay, so it means you assume that QB and QA are the inputs and DB and DA are the outputs. Okay, so just like we used to do it in combinational circuits, right? So you have an output Y, you represent it as function of XYZ, right, where XYZs are the input. So similarly I'm doing the same thing here as well. So is that clear, Omkar? Okay. Okay, so what I did is, so here I observed that okay, 0 0 is there, so I just write the equivalent decimal form. 0 1 1 I wrote it as 3, 0 1 I wrote it as 1, 1 0 I wrote it as 2. Okay, so I wrote DB and I just observed at which locations dB equals to 1, and those locations I marked as summation of dB 0 and 1. Similarly, I'll do the same thing for dA. So dA is equal to summation of 0 and 3. Okay, so now let us write out the equation. dB is equal to, if it is 0 0, it means QB bar QA bar plus 0 1. So 0 1 means QB bar and QA. So this, if I take QB bar common, then I am left with multiplied by QA plus QA bar. So X plus X bar is 1, right? So this will be QB bar. So dB is QB bar. Okay. Similarly, if I write dA's equation, I have summation of 0 and 3. So 0 means QB bar QA bar and 3 means QB QA. So this is my equation for dA. Okay. So let us see out of the following options which one is correct. So I get QA bar QB bar plus QB QA as dA. Okay. Then dB is QB bar. So option D is correct. Okay. So it means if I give my D flip-flops this particular input, then I am going to achieve this particular sequence of counting. Okay. Is this question clear, and the approach that I used to explain this question? Does anyone have any doubt? If anyone has any doubt in this question, they can feel free to ask. So, should I assume that everyone is clear?
Yes.
Okay. Okay, then we can move to the next question. That is question number 7. This is question number 8. Okay, so question number 8. So what we need to do is we need to mention a feature that distinguishes the JK flip-flop from the SR flip-flop. Okay, so preset input, it can be there in either of the flip-flop. Type of the clock, it can be, okay, we have an answer. Yeah, so the answer is correct.
A is the answer, yeah.
Correct. So the toggle condition when J is equal to 1, K is equal to 1, that is the feature that distinguishes JK flip-flop from the SR flip-flop. Okay. Yeah. So this question I would like you to answer. So you have a 4-bit counter and you have to figure out what is the value of n. Yeah, correct. So the answer is 15. Okay. So let's say n can be anything. So there is a general formula. So let's say you are going to count let's say there exists a n-bit counter. N can be anything. So the terminal value is going to be 2 to the power n minus 1. Okay, so just like in this case, if it is 4-bit, then you just write 2 to the power 4, that is 16, minus 1, that is 50. Okay, so this was a straightforward question, but okay. Okay, so can anyone answer this question? Okay, we have one answer. So Okay.
C may be the right answer. C.
Mm, okay. So we have two answers. Means okay. Why? Okay. Why will it be C?
The question is from 0 to 1, that's why it's striking that C may be the answer.
Okay. So yeah, this is a bit confusing, but what I want you to realize is from you have to make the transition from 0 to 1. It means that 0 value is already present at the output. Okay. So you just need to arrive at this value 1. So what you need to do is you need to toggle it. Okay. So option B is correct. Okay. I hope this part is clear.
Yeah.
Okay. Okay, so try to answer this question that there are 8 T flip-flops that are connected to form a counter. What is the maximum number of states possible for the counter? Okay, we have one answer. Any other answer? Okay, so there are 8 T flip-flops that are used to form a counter, and 2 to the power 8 minus 1. Okay. Okay, yeah, that's actually a
Is it
different.
4095?
4095. No, no, that's a. I think from the right answer you have means exceeded the yeah value. So probably it's a bit lesser than the answer, but yeah. So actually here I'll explain two things. So see, there are two answers that I can see on the chat box. One answer says 256, another answer says 2 to the power 8 minus 1. Okay. So whenever you are asked the maximum number of states possible, okay, for a counter, so the correct answer is 2 to the power n. Okay. So here it is 2 to the power 8, that is 256. Okay. Whenever maximum number of states are asked. But I received another answer which says 2 to the power 8 minus 1. So whenever it is asked what is the maximum value or the terminal state that can be achieved, that is actually 2 to the power n minus 1. Okay, it means 255. Correct? But when you have to mention all the states, so all the states is going to include the 00000 wala state, that is 8 bit 0. Okay, so then you have to say that total 256 maximum number of states are possible. Is that clear? Amit, is that clear? Okay, yeah, okay, great. So please make sure that you don't get confused between these two things. Okay. Okay, so the next question is related to okay, you need to figure out the output Y, okay, of this particular PLA circuit. Okay, so start with, let's say I am calling this as 1, this is 2, this is 3, this is 4. What is 1?
A bar, B bar, C.
A bar, B
Oh,
bar.
sorry. One.
Yeah.
You are asking about one. So
Yes,
A
yes.
bar, B, C.
A bar, B,
C.
C. Does everyone agree to this? Okay. Okay, so 1 is A bar, B, C. What is 2?
A, B bar, C.
A, B bar, C. Okay, does everyone agree, or is there anyone contesting this answer? Okay, I assume that. Okay, yeah. So what is the third number?
A, B, C bar.
A, B, C bar. Okay. What is the fourth one?
A, ABC.
ABC. Correct. So we can see that there is an OR gate. Okay. So whatever terms we arrived at, we just need to take the OR of that. A bar B C plus A B bar C plus A B C bar plus A B C. So this is the expression of Y output. Okay. Does anyone have any doubt in this question, or is everyone clear? Okay, Amit, do you have a doubt?
No, sir.
Okay, great. Okay, so yeah, these were the set of problems that I planned for today. Let's revisit whatever we did today. Okay, and yeah, so the solutions as well as this particular video recording is available on the YouTube channel, so you can go through it to revisit what methods we did to solve it. And these annotated slides will also be uploaded by the NPTEL team. Okay, you can go through them, and while going through them, so try to do everything on your own, and then only look at the solution, the approach that we used. Okay, so let us revisit what we did today. So the first question was related to finding out the output frequency of the flip-flop. Okay, the first thing that we did is we saw the truth table, how it works, and we also reduced the truth table to a form. Okay, so that it becomes a function of only J and K, and Q plus is represented in the present state format. Okay, and after observing this, we saw what happens when J is equal to 1 and K is equal to 1. That is the condition that was assigned to us. Okay, then what we did is we started drawing the clock diagram, the timing diagram, right? So from this timing diagram, we figured out that if the clock is having a frequency T, we observe that the output Q actually has a time period 2T. Okay, so if the clock's time period is T, the output of the Q is having a time period of 2T, which means that effectively the frequency is being reduced by half. Okay, and this observation we tried to generalize it for any number of flip-flops. Okay, then I mentioned that what if this particular output is acting as a clock to another flip-flop. Okay, and we observed that if that is the case, then the next flip-flop, again the frequency gets divided by 2, right? So it becomes f clock by 4. Similarly, we can use this particular generalized formula if we have n such flip-flops that are cascaded in this way, then the output frequency of that clock will be f clock by 2 to the power n. Okay, then the next thing that we observed is how many flip-flop circuits are needed to construct mod 16 counter. Okay, so there is a follow-up question to this one in question number 6, I guess. So that was mentioning about mod 5 counter. So there also you need to use the same logic. Okay, so someone was facing an issue in this question, that's why I thought I'll mention mod 5, which was mentioned there, that two cascaded mod 2 and mod 5 are there. So okay, so here we needed to say how many flip-flops. So what we need to figure out is what is going to be the terminal state. So terminal state is going to be 1 1 1 1, that is 15, because it counts from 0 0 0 to 15. So for the terminal state we will need 4 bits. Because we need 4 bits, we will need 4 flip-flop to store those 4 bits. So the answer to this question is 4. Okay, so similarly we can also use this particular formula to arrive at the lowest n that satisfies this condition. Okay, so yeah, so the lowest n was 4. Okay, and this is another example that I was giving. Suppose it says mod 14 count, then you need to solve this particular equation and arrive at the lowest integer value of n that is going to tell you how many flip-flops are needed. Okay, then the next question that we saw is we were given a flip-flop configuration and we were supposed to tell what this circuit was doing. So in the previous cases what we did is we directly drew the timing diagrams, but timing diagram is a form of drawing and it may be a bit cumbersome to draw that. So instead we can also rely on truth tables. So what I did is I used a truth table where I took whatever input. So this is basically clock. Okay, so whatever input are presented to the truth table and whatever is the output. So clock and D was the input and Q and Q bar were the output. Okay, and we saw that D is being fed by Q bar. Okay, so it means whatever Q bar value is arrived at, so that value will be fed to D in the next clock. Right, so that is what happened, that here D becomes 1 because previously Q bar was 1. So here D becomes 0 because previously Q bar was 0. And we observe that with respect to clock, the Q transitions in this way. It becomes 0, then 1, then 0, then 1, right? So it is basically following a 1-bit counter structure. Okay, so this is option C was correct. Okay, so question 4 was actually a follow-up question from question number 1. So if you are able to realize that t is equal to 1 is the same condition as j is equal to 1 and k is equal to 1, then this question is a cakewalk, because you have already seen that the formula that we arrived at for generalizing that output frequency is fn by 2 to the power n. We see that there are 3 flip-flops, so we write 2 to the power 3, then we arrived at 125 as the answer. Okay, but if you want to proceed logically, then you can state that okay, here there is one flip-flop, so the frequency will be halved. So here there is another flip-flop, the frequency will be further halved, so 500 to 250. Then there is a terminal flip-flop, so the frequency will be again halved. Okay, so we arrive at the answer 125. In both the ways you can arrive, whichever you find comfortable, you can proceed with that. Okay, so the next question was related to cascading of two counters. So one counter was mod 2 counter. So whenever anything mod n is written, it means it will have n states. So mod 2 means 2 states, 0 and 1. Mod 5 means 5 states, 0, 1, 2, 3, 4. Okay, and because the terminal state was 4, so 4 needed 3 bits for representation. Okay, so that was just a trivial question. So 4 can be represented as 1, 0, 0, and so that's why we needed 3 flip-flops, right? And when we are cascading these 2 flip-flops, we needed to figure out what is the modulus, what is the mod of this newly constructed counter, mod x. Okay, so the formula that I mentioned is if you are cascading 2 flip-flops, mod A and mod B, then mod x will be equal to mod A into B. Okay, and then using the timing diagram I explained how we arrive at that particular result, and the observation that we make, that if we are feeding f clock, what is the fx, what is the frequency of not frequency but what is the mod of that fx that we arrive at. Okay, then the next question was related to the behavior of j and k flip flop, jk flip flop. So here we needed to figure out that if the input, if the q is 1, then what input can be applied to make it q plus is equal to 0. Okay, so there were two possible conditions, one in which j is equal to 0, k is equal to 1. So in that condition, irrespective of what the present state is, the next state is going to be 0. Then we had another condition, if both j is equal to 1, k is equal to 1, q is going to be the q plus is going to be q bar, and because in this case 1 was given, so q bar will become 0. So that also satisfies our condition, but the option that was given to us is only 1, so j is equal to 1, k is equal to 1, and using the clock. Okay, so in the next question what we did, so we were supposed to figure out what should be the input to the D flip-flops, like we call DA and DB, to represent the two different bits of the D flip-flop. Okay, and we had to arrive at this sequence 0 0 1 1 0 1 and 1 0. Okay, then here we observed how to try to solve this question. The first point, the very important point in this question, is how to interpret this question. We need to figure out what this question wants from us. So this just wants what is going to be the input to DA and DB, right? And based on that we need to figure out, the first thing that we did is we constructed this truth table. So present state, next state, and the D in column. So the D in column represents what D input should be applied for each of the conditions to arrive at the next state, and then we solved for what is going to be the DB. Okay, so DB and DA are going to be functions of QB and QA, and we had to figure out, so what is the possible combination which we need to take care of so that DB is equal to 1 or DA is equal to 1. Then we formed those conditions, we reduced them, we simplified them, and we arrived at the answer as option number D. Okay, then this is a factual question. So the feature that distinguishes JK flip-flop from the SR flip-flop, it is basically the presence of toggle condition. Okay, then the next question was also a repetition of the previous questions. So in this question we needed to find out what is the terminal state. So here the terminal state is 15, the maximum value that 4-bit counter can arrive at. The next question was related to the state transition of T flip-flop from 0 to 1. Okay, so if the state is already 0 and we needed to transfer it to 1, so toggle flip-flop at T is equal to 1 will actually toggle your state. So that is the answer to this question. And in next question we were supposed to find out what are the maximum number of states possible for the counter. So that is basically 2 to the power n, and in this case n was 8, that is 256. Okay, so then there was another point which someone mentioned, that why it is not 2 to the power n minus 1. So yeah, 2 to the power n minus 1 is the terminal state, that is the maximum value of the state, not the maximum number of states. Okay, so you need to distinguish between these two conditions and then only answer accordingly. Then the last question that we solved was related to PLA, and we were supposed to come up with the expression for Y output. So here we just observe which ones are connected with the AND gate, and after figuring out the ones that are connected with the AND gate, we represent the equations for 1, 2, 3 and 4. Okay, and what we do is we take the OR of that, because Y is basically the OR of those expressions. Okay, so these were the questions that were covered today, and if anyone has any doubt, they can let me know. So please try to go through these questions on your own, and let me know if anyone is facing any difficulty. So you can use the forum that is provided in the NPTEL ask a question section, so you can ask your question related to today's session there. Okay, and yeah, so if anyone has any doubt, they can unmute themselves and ask me the question. So whatever we covered, I hope that will be helpful for you to solve your assignments. Okay, and yeah, so these were the 12 questions that I planned to solve today. Does anyone have any doubt or any query that they want to ask? Okay. Okay, then I'll be here. Just let me know if anyone has any doubt. Else, that's the end of today's session. Okay. No, I'll request you to stick to today's discussion only. So I don't know whether these things have been covered or not. Anything related to today's session? Thanks everyone for joining. Yep. Okay. I'll be here around. Just let me know if you have any question. Okay. Thanks everyone. If anyone has any question, they can let me know. So any doubt related to whatever we covered today. So